All right, guys, today moving on to section 2. How we're going to finish up our unit is going to be with a few specific discrete probability distributions. In section 1, we worked with kind of just the generic. What is a discrete probability distribution? How do we find the mean? How do we find variance, standard deviation, expectation, all that good stuff. Now today we're going to focus on a specific type of discrete probability distribution. It has specific properties, and we talked earlier when we introduced probability distributions, some of them can be represented by formulas, and we're going to see that today with our first specific type. All right, so our binomial distribution, it's a discrete probability distribution. It has the following properties. Here we go. The experiment consists of a fixed number of identical trials. And we just use the generic N for number of trials. N in the past has been our sample size, our total number of data values. Now in this case, N is our total number of trials. And notice it says identical, so I have to do the same thing trial after trial after trial. I can't change or alter anything. So it has a fixed number of trials. So we're going to say we're going to roll the dice 7 times. We're going to select 10 students. We're going to test 15 light bulbs. It has to be set out how many trials you have. Each trial is independent of the others. So each outcome, each trial does not affect the other trials. So that means everything is going to need to be done with replacement. Everything needs to be done with replacement on that if we are selecting things. For each trial, there are only 2 possible outcomes. One outcome is labeled a success, and the other is labeled as a failure. So the success is the outcome that you're specifically looking at, and then the failure will be whatever the other one is. So only 2 outcomes. Nice little helpful hint with how this is named. The prefix by means 2. So I can only have 2 outcomes. We're limited to that. For every trial, the probability of getting a success is labeled P. The probability of getting a failure is 1 minus P. It's just that complement piece. There's only 2 outcomes. So if I put the probability of success together with the probability of failure, it needs to equal 1. There's only 2 outcomes. There's nothing else. So my probability has to equal 1. The binomial random variable was represented by X. That counts the number of successes in your trials. So how many successes are you looking for? That's going to be our X. Little p represents the probability of that success. X represents how many times we're looking to have that success happen, and however many trials we have selected. Now we had just our generic discrete probability distributions. We also found things like mean, variance, and standard deviation. We can do that with the binomial distribution as well. And I already have that filled in on your sheet. I like to have formulas filled in already for you. So you have the mean and the variance. So if you needed standard deviation, just square root the variance if you were to need that. So this one has those special little formulas. They're different than the ones we were using when we just had those generic discrete probability distributions. This is a specific type. So in order for us to be like, well, hey, this situation, this experiment I have, can it be considered binomial? Those properties have to be met. If the properties are met, you can use the formula we're going to talk about today. If the properties can't be met, it might be one of the other distributions we're going to talk about later in the unit, or it might just be that generic one that we've been working with. So if the properties aren't all met, we cannot consider it binomial. It might be one of the other ones we're going to talk about, or it might just be the generic one we worked with in the first section. So we'll talk about that as we get further along in our unit. So let's look at our first example, one that we are already familiar with. We have a coin being tossed 3 times. Find the probability of getting exactly 2 heads. Now, the way we've been solving this is by a sample space. Up to this point, we haven't quite put together yet how to do something like this without the sample space, and that's what we're going to look at today. I'm just going to click just so I can see my space. So we're going to solve using the sample space. If we want to make a tree diagram, we can, kind of up to you. I'll go ahead and make a tree diagram. If you like making tree diagrams, feel free to make one on yours as well. So in the past, this is how we would have solved this question. We would have created our sample space. Tree diagram, maybe you just chose to list them out. That's fine. Up to you. I saw a wide variety on the Unit 4 test and a lot of success with finding the sample space, so up to you. There's our tree diagram. So our sample space, I'm going to go ahead and list it here. The order you list your sample space in doesn't matter, so if you chose to not do a tree diagram, that's okay. The order you have yours listed in might be different from mine, and that's okay. Tree diagrams, again, just make sure we get all the unique outcomes needed. So we should have the total of 8 outcomes. So the probability of getting exactly 2 heads, so probability 2 heads, it says exactly 2, so we've got 1, 2, looks like 3 outcomes out of our 8. And this is typically how we would have handled this type of question. We would create our sample space, and then we would just find that theoretical probability. Now we want to ask ourselves, though, could this be considered a binomial experiment? So in order to see if it is or not, we've got to go through that checklist of steps that we had on that first slide. So the first step was, are there a fixed number of trials? Oh, bad animation. There are a fixed number of trials, and that's, should say 3. We're going to flip the coin 3 times. Did I have 3? I have 3 on your sheet. I don't know why it's not 3 on mine. There are a fixed number of trials. That's the first property. There has to be a fixed number of trials. Second one says each trial is independent of the others. So each trial is independent. That means the outcome of one toss does not affect the outcome of any other tosses. So if I get heads on the first toss, it doesn't affect what could happen on the second or third. So all the trials are independent. The third property, you can only have 2 outcomes for each trial. Each trial, each toss is either heads or tails. Those are my 2. For every trial, the probability of success, we label that as P, and it's the same for each trial. Our P in this case would be 1/2. Success would be heads in this case. Then number 5, we need what is our X going to be, and X is the number of heads tossed in. I had changed my example. I fixed it on your sheet, but for some reason I didn't fix it on mine. So X is going to be the number of heads tossed in those 3 trials is what we're looking for. So this one could be considered binomial. So instead of having to draw out the sample space, we can come up with our formula and make these a little quicker, a little easier. All right, so since we want exactly 2 heads, heads in this case is success, and 1 tails, and I forgot to change that on yours. You want 2 heads, you want 1 tails. I was going to do 4 tosses of the coin, but I'm like, well, we don't need that big of a sample space. We can get it across with 3 tosses. So, little typo there. Please fix that on your sheet. So, since we want exactly 2 heads, which are considered successes, and 1 tails, that's our failure, the probability that that happens, and this is what a lot of us just wanted to do back in Unit 4, like, Miss Golly, so I want 2 heads and a tails. So, it should just be 1/8. But if we look at our sample space, though, we know we're supposed to have 3/8. We know it happens 3 times. So this was the piece that was kind of missing for us in our last unit when we just started with probability. So here's what we have to think about, though. We have to consider where those different heads can happen at. And that was the part that we had to think about in Unit 4, and that's where our sample space came in handy. The sample space just made it much quicker and easier instead of thinking about all those different ways. And thinking about those different ways, we actually end up pretty much creating our sample space to come up with that. So what we can do, though, is we can consider, though, to get that 3 that we need, we can take the number of combinations, 3 things, we're taking 2 at a time. So 3 things, we want to make 2 of them heads. So of the 3 tosses, we want to make 2 of them heads. So that can happen, and the little formula, I just showed it out. We have a 3C2, and we come up with those 3 different ways. So if I have 3 tosses of the coin, I want to make 2 of them heads. 3 tosses of the coin, I want to make 2 of them heads. So there's the piece we're missing. So we're going to put together that combination piece with our multiplication piece. So we're going to put our combinations together with that multiplication rule that we saw. We saw both of those things last unit. So if you have a binomial distribution, you have a binomial experiment, all of our properties are met. I'm going to show you next the little formula you can use instead of having to draw out that whole sample space and trying to think about how many different ways things can happen. So the little formula that we have, I think I already have this on your sheet for you. I do. But the part I don't have filled in for you is what each little piece up there means. Now the formula, I'll be very honest, it looks a little more confusing than what it actually is. Once we start putting it into action, all the pieces will become more familiar. So X is the number of successes. You have to be careful in thinking about successes. Successes don't always translate into what we think of as a success in life. So heads versus tails, well, in real life situations, like, well, neither one's really a success or a failure. We have to take it as the success is, what's the outcome we're looking for? In this case, we were looking for heads. So it's not always necessarily a literal success, like we won the game. It's not always necessarily a literal success. All right, N then is the number of trials. P is the probability of getting a success on any trial. So that little lowercase p, I know we're used to capital P for probability, so hopefully it's not too big of a jump for us to go to that little lowercase p. All right, so that is our little formula. What I want to do is just spend some time now going through a few examples, and I'll go ahead and I'll jot the little formula up here on the board. Sorry guys, you're going to flip your sheet. And then the examples are on the back. So I'm going to put this up on the board real quick. X. There we go. All right, so I've got the formula up on the board, so you have to keep flipping back and forth. So let's look at our second example. 90% of graduates at State University who apply to a particular medical school are admitted. This year, 6 graduates from State University have applied for admission to medical school. Find the probability that only 4 of them will get in. So let's first of all talk about, and I get it, it's an example, so yep, let's just fly into the formula. But we're going to have other distributions we're going to talk about. So we have to make sure we can pick out that the binomial is the one to use. So we have to first of all ask ourselves, do we have a fixed number of trials? What's considered a trial in this case? What do you think? What's a trial? A trial is that they apply. Yeah. So each application is a trial. Do we have a fixed number of them?
6.
Yeah, we got 6. So property 1, check. We've got 6. Property 2, is each trial independent of the others? So does the first application have any effect on the second one, or the third, or the fourth? No? So property 2 is okay. For each trial, there's only 2 possible outcomes. What can happen when they apply? They get in, or they don't. 2 outcomes. Property 3, check. And then we have, for every trial, we have that same probability of success. What's considered our probability of success? The 90%, right? So this is our success. 1 minus P is going to be our failure. So success in this case is they are admitted. Failure is not admitted. Now in this particular instance, this is a literal success failure. Success is getting in, failure would not be. They won't always be that way. We'll see an example next that it's not that way. All right, then we have the binomial random variable x counts the number of successes we want. So let's look at our first example. Let's get into our first one. So at that point, guys, we've checked all the boxes we need to for a binomial. We have a fixed number of trials. Each trial is independent. There's only 2 outcomes. We have a probability for success. And it stays the same for every trial. All right, so let's look at the first one. Find the probability that only 4 get in. All right, so we've got our formula. I've got it up on the board. So probability x equals 4. So what's the probability we get 4 successes? Now, if we need to, we can label. We have an n. N is our total number of trials. We had 6 applicants. The R that we're going to choose, because we had an NCR, is going to be, which R we could actually replace with an X. And we already have the P labeled, but we'll put it down here for the example. And then we have 1 minus P is our 10%. And I think that covers everything from our little formula. It does. All right, so here we go. The first part of our formula, we have an NCR. So I have 6 trials, 6 applicants. I'm going to choose 4 of them as successes, which in this case, that they get in. Times, we have our lowercase p, which is probability of success. The exponent for the probability of success is how many successes we want. That's our x. Probability of success, how many do we want? We want 4. Then we're multiplying by the probability of failure, which was that 10%. And then I know you look at the exponent in the formula, like n minus x, that's how many are left? We wanted 4 successes. and 2 failures. 4 successes, 2 failures. That's how you get the exponent. So 6 total applicants. 6 total applicants. We're choosing 4 of them to get in. 90% chance you get in. You want 4 of those. 10% chance you don't get in. You want 2 of those. That's where the exponents come from. So now take a second. Try it out in your calculator. If you need one of mine, you may borrow one of mine. You can do these on just the basic ones I have. Double check me when I do this. I get this exact answer. I don't know if it's going to go, nope, and it's not going to go to a fraction for me. So part of it is, can you recognize it's a binomial? And then the other part is actually setting it up and doing the computation. I won't have time to check these now.
All right, that's fine.
So I'll have to check them and I'll let you know, okay? So when you have just an exact amount, the formula, once you do a little practice, the formula is pretty straightforward. But now I wanted to make sure, and we'll do a couple examples today, that we bring back a couple of those phrases that some of us still struggled with on that Unit 4 test. The idea of at most and the idea of at least. If I want at most 2, and I'll put the 2 in there as well. At most 2, how many does that mean? 0 or 1 or 2. 0 or 1 or 2. So we have those 3 different situations that we have to look at. 0 or 1 or 2. So that's going to be P of, we have capital X, and if it's at most 2, that means we're going to be less than or equal to 2. So when you do your notation, you're going to want to use that inequality symbol, not list out 0 or 1 or 2. You want that at most 2. So X has to be less than or equal to 2. So what that means for us is we see that keyword or. This is something we saw a lot in Unit 4. Keyword or is going to tell me I have to do what with those 3? I have to add. Yep, you have to add those together. So let's start with 0 get in. Let's start with 0 get in. So I have 6 applicants. I'm going to choose 0 of them to get in. And I'll be honest, the words I'm saying out loud, that's what I say in my own head when I do these. Or if I'm by myself, sometimes I do say it out loud. I have 6 applicants. I'm choosing 0 to get in. Probability of success. If you just want to do 0.9, if you don't want the extra 0, you don't need it. I was putting it so we saw the connection with the 90. 90% that we get in, I want 0 of those. 10% we don't get in, I want all 6 of them. So when you're using this formula, you just have to match up how many successes you want versus how many failures. So you have to match up the probabilities with each amount. That's how you get your exponent. Your exponent is the amount of successes or the amount of failures that we're looking to have. Yeah?
Wait, so could you use 2 in it?
We are going to be using 2. We're going to use the one next. You could start with 2 if you wanted to. So this is our 0 get in. Now we need to add that to 1 gets in. So remember that at most piece, we've got 3 different things to look at. We have the 0. Now we want 1 to get in. So 6 applicants, I'm going to choose 1. 6, choose 1. Then we're going to have our 90%. Oops, forgot my 0. And we want one of them. So however many you're choosing with that combination, that's going to be your exponent for your successes. Those two are always going to match. Then we have our 10%, and we're going to have 5 of those. 1 gets in, 5 do not. So this is our 1 gets in. Last but not least, we need to do the 2. Again, the reason we're adding is because we're going to have 0 or 1 or 2. So now we want 2 to get in. So we have 6, and we're going to choose 2 to get in. 90% chance they get in. We're going to have 2 of those. 10% chance they don't get in. We're going to have 4. And then this is our 2. 2 get in. So for that at most piece, we need all 3 of those cases, not just 2. That's what happened to some of us on our Unit 4 test when we saw at most 2. We found the probability for exactly 2, and then we moved on. So I want to make sure we revisit that at most today. And these can take a little bit. 60, 0. Give me just a second here. If you want to verify with me, double check for me. Just in case. Times 0.5 plus. All right, when I did this, maybe somebody can double check. I know it's a lot to enter in. That's what I came up with. Now, is it easy to miss a exponent here or there or an addition sign? It can be. So always make sure, especially come test time, make sure first of all that you show your work. Here's what should have went in my calculator. Here's what I got out. Okay, always make sure you're showing your work. Let's do one more together. I want to give you guys a chance just to try a few today. Find the probability that at least 2 will get in. At least 2. So let's talk about that. Before we start setting anything up, let's talk about what that at least means. At least 2 is going to mean 2 or 3 or 4 or 5 or 6. Now, I know we talked about this last unit. If you want to, you can do the same thing we did in the last part for 2 get in, 3, 4, 5, 6. You can set up that formula for all 5 of those cases and add them together. Absolutely, you can. It's the longer way, but you can. Or we can talk about the complement. What are the only amount of people getting in that we don't consider? 1 or 0. So you can do this. You can do probability. Now in this case, x is greater than or equal to 2. You can do all 5 cases. You can set them up like the ones we did up above. Set it up for all 5. I want to show you the shortcut. You can do the long way. Absolutely more than welcome to. But you'd be lucky that we're just picking 6. What if we had, it's a university. What if 50 people applied? That's going to take a lot to add those all up. So let's talk complement. So what we can do is we can do 1 minus that 0 or 1. So now we only have to do 2 setups. We do a little subtracting. Again, you can do the long way if you want. You're more than welcome to. So here we go. We're going to do 1 minus. I'm going to start with that 0 get in. We have that up above already. We actually have the 1 up above too. So this would be that 0 get in. So 6 failures, 0 successes, 6 failures. And we're going to add to that 1 success. Make sure your addition happens first. So we're not going to do the 1 minus piece until we've figured out the 0 probability that 0 get in, the probability that 1 gets in. So make sure you have it set up that way. If you're going to enter everything in your calculator at once, make sure you're using some parentheses. I'm going to do this real quick. If you want to practice on yours, have at it. And if I've got something wrong, guys, let me know. I can misenter something just as easily as you can. Alright, so I get when I do this, I'm going to write out the whole thing. And that's what I came up with. Now again, you could do the whole setup for 2, for 3, for 4, for 5, for 6, and add them. You can. That's what at least means. That's what at least 2 means. It's 3, 2, or 3, or 4, or 5, or 6. I don't want to do all that setting up, so that's why I do the complement. Now, before I give you guys a chance to try that last set of examples that I have on your sheet, I do want to show you, if you have the graphing calculators, and I'm sorry, that's only available on the graphing ones, it doesn't work on my little ones over on the table. I just want to show you real quick, if my calculator will cooperate, or my computer for that matter. There is a shortcut. Here we go. So this might, once you see some of these shortcuts, this might sway you to try to find your graphing calculator that you used in Algebra 2. Alright, so let's do just the first part I want to show you. If you're going to have exactly 4, so if you have exactly an amount, not a greater than or less than, but exactly an amount, you're going to press the second key, and feel free to write these steps down if you'd like. You're going to press the second key and then the vars key. Notice up above the vars key, it has DISTR. That's our distribution menu.
Where's the vars key at?
It's highlighted red on my screen. It is underneath the arrow keys. Notice up above the vars key again, it has the DISTR. That means distribution. This is our distribution menu. Now, if you arrow And for everybody, it's, sorry guys, it's kind of glitchy. Everybody's calculators, it's a little different. On this operating system, mine, binomials, look, it has binom. Mine's the capital A and the capital B. Some of the older operating systems don't have all of these menu options, and that's okay, we're not going to need all of them. There's two different labeled as binomial. There's binom PDF and there's binom CDF. The PDF one, sorry guys, my mouse isn't working. The binom PDF one is what we want for just one exact value of successes. So I'm going to go binom PDF. My number of trials, that's how many applicants we had. We had 6. Probability of success. You need to make sure you either enter that in decimal or fraction form. We can't put 90 in there. You have to actually enter the probability. So 0.9. The X value is how many successes you want. We wanted 4. We wanted 4 to get in. Sorry, guys. There we go. All right. So 6 trials, probability of success is 0.9. I want 4 successes. That's the X value. If I hit enter, it's going to paste it. Now, if you have an older operating system that didn't bring up the menu we just had, if you had binom PDF just pop up on your screen, this is what you need to enter. 6, 0.9, 4. How many total trials? Probability of success, how many successes you want. So if you have an older operating system, I know some of you have TI-83s, this is how you have to enter. It doesn't give you those options. Press enter, and there's our matching probability. So can you use this shortcut on a test? Absolutely. If you're going to, though, I still encourage you to show your setup, or at least show me this part, the binom, PDF, and the information in the parentheses. At least show me that part. Because if all you give me is a wrong answer, all I can do is mark it wrong. And I won't have any idea what pieces you understand and what pieces you don't for that particular formula. Now, there was another option on our screen, and we're going to look at that for the second part of that example. It was binom CDF. How I remember this one, the C to me stands for cumulative. The binom CDF one will find all the probabilities for you, starting with 0 and going up to the number you put in for X. So our number of trials, still 6. Probability, still 90%. Now the X value you put in, and again, feel free to make notes on your sheet. This feature will add together all the probabilities for 0 successes up to and including the value you put in for X. So my setup right now, since it's the CDF, C for cumulative, this will add together for me 0 successes plus 1 success plus 2. It will always start with 0 and add and continue until the X value you tell it to stop at. So this is 0, 1, or 2. That's what we did in the second part of this example. Paste it. If you have an older operating system, this is what you would have on your screen. Binom CDF, 6 trials, 90% probability of success. We want everything 0 through 2. I hit enter. So 0 through 2. Yeah.
For the at least, did you just take 1 minus
Mm-hmm. So now if you're thinking, wow, that's way easier, right? So now how can we handle the last situation? I can't tell the calculator to start at, what do we start at, 2? I can't tell the calculator to start at 2 and stop at 6. This program only will do 0 up into the number you tell it to stop. So if you want to use the calculator, you sure can. You're going to have to do, though, the 1 minus option. Go to binom CDF. Six trials, 90% probability of success. But now this time, though, we want to subtract out 0 or 1. So we need to tell it to stop at 1. So again, you can use this feature for the at leasts, but you have to do the complement choice. You have to do the 1 minus the complement to use this calculator feature. 1 minus, we hit enter, there's our matching probability. You are more than welcome to write these all out and enter them all in the calculator with the combinations and the exponents and all those things. You're also more than welcome for that option too. Okay. So to finish up today, there is one set of examples on your sheet that are left. I will put the answers up as soon as I get those up for you. There we go. If you want to use the calculator shortcuts, you can. My keyboard quit working. There we go. Here's what you have to be careful. Starting out, I just want to make sure we all get a good start on this. The success for the first part is that they're not defective. The probability you're getting deals with defective. So just be careful. Make sure you have the right p-value. Make sure you have the right p-value. Just be careful on that.
Miss Colin.
Yeah.
Why did we put 1 for this when we were trying to find
Because we want 0 and 1.
0 and 1?
Mm-hmm.
Okay.
So you have to tell it to stop.
Stop there.
Yeah.
But then since we're doing the 1 minus that, it makes it so that it works.
Right.
Okay.
Because you need to do 1 minus that.
Okay.
If you want to do the calculator way.
Okay.
You have to do 1 minus. Yep.
Sit back and fill up my water.
Oops. So be careful on the first part. I want 3 tires that are not defective. From the question, I know that 20 out of 100 are. I know 20% are defective. So if I want not defective, I need that 80% as my success. So you have to make sure when you're setting things up, you might have to use a complement here or there. So just be careful on that. Now figure out what these are real quick. If you want to do the calculator shortcut, you can. And also be careful on this. You're not selecting 100 tires. You are selecting 5. You're not selecting 100 tires, you're only selecting 5. The 100 you use to get your probability of success and failure. So just be careful on that. And then in the second part, it switches back to being defective. So make sure you've got the right check yours with mine. If you disagree with something, let me know. I can very easily hit something wrong in the calculator. Definitely.